Assalamualaikum and good day. We are Group 1 from class AS2392A. Today, we will present our workplace assessment for course IHS 421 Chemical Health Risk Assessment. This assessment was conducted to identify chemical hazards to health used in the laboratory, evaluate the possible exposure risk, and assess whether the existing control measures are adequate. Our group consists of 8 members as shown on the slide. Each member contributed to different parts of the assessment, including workplace observation, collection of safety data sheets, hazard and exposure assessment, evaluation of control measures, and preparation of the report and presentation. Now, we will begin with an overview of our CHRA presentation. For today's presentation, we will cover 5 main sections. First, we will explain the objective and scope of CHRA. Next, we will describe the worksite and the specific work unit that was assessed. We will then explain the assessment methods used, followed by the main assessment findings and results. Finally, we will present our recommendations and the actions that should be taken to improve chemical safety in the laboratory. The main objective of the CHRA was to identify and assess the health risks associated with chemicals used during laboratory activities. First, we compiled information on the chemical hazards to health and were used during the practical and research work. We then determined the hazard rating of each chemical by referring to the relevant safety data sheets and chemical hazard classification. The exposure of the similar risk group were also evaluated by considering factors such as chemical volatility, duration of handling, and frequency of the activities. In addition, we assessed the adequacy of the existing engineering controls, ventilation systems, administrative procedures, and personal protective equipment. Based on the assessment findings, suitable risk reduction measures were recommended in accordance with industrial hygiene practices and relevant Malaysian requirements. Next, my colleague will explain the worksite and work unit that were assessed.
The workplace selected for this assessment was Magma Analysis Forensic, located in room OM114 at the Faculty of Applied Sciences, UiTM Shah Alam. The laboratory is used for forensic teaching and research activity involving chemical, biological, and physical samples. The work unit assessed involved 1 female laboratory assistant who normally worked from 8 a.m. until 5 p.m., equivalent to approximately 8 working hours per day and 5 days per week. The main activity assessed included sample aliquoting and preparation, the addition of organic solvent and mineral acid for taxing and centrifugation, phase separation, and solvent evaporation. The assessment also covered sample reconstitution for GCMS or HPLC analysis, as well as chemical waste handling. These activities were selected because they involve direct handling of chemical hazards to health and may result in worker exposure. During the assessment, several potential exposure points were identified. Exposure may occur during manual pouring, pipetting, and dispensing of chemicals. Workers may also be exposed when opening vials after agitation or centrifugation because vapors, droplets, or small amount of aerosols may be released. Solvent evaporation and concentration may generate chemical vapors, particularly when volatile solvents are used. Accidental spill may also result in skin contact, especially during chemical transfer, sample preparation, and waste handling. The laboratory currently provides several safety facilities, including ducted chemical fume hood, chemical storage cabinets, and a safety shower and emergency eye wash station. These facilities are important for reducing exposure and responding to chemical incidents. However, their adequacy and actual use must still be evaluated as part of the CHRA. Next, the assessment methodology will be explained.
The CHRA was conducted using 10 main assessment steps. The first step was to gather relevant information about the workplace. This included the chemical inventory, work activities, exposed personnel, safety data sheets, and existing control measures. The second step was to divide the workplace into specific work units. The division was made based on similar tasks, chemicals used, and exposure conditions. This allowed the assessment to focus specifically on workers who experience similar chemical exposure patterns. The third step was to determine the degree of hazard of each chemical hazardous to health. The hazard rating was determined by reviewing the chemical classification, health effects, and hazard information provided in the safety data sheets. The fourth step was to evaluate worker exposure through all possible routes. The assessment considered inhalation of chemical vapors, skin contact during handling or spills, and accidental ingestion resulting from poor hygiene practices. The fifth step was to determine the level of risk. The risk level was determined by considering both the degree of chemical hazard and the estimated level of worker exposure during the activities. The sixth step was to assess the adequacy of the existing control measures. This included examining the engineering controls, work procedures, personal protective equipment, and other preventive measures provided in the laboratory. The purpose was to determine whether these controls were suitable, properly used, and sufficient to protect exposed personnel. My teammate will continue with the remaining assessment steps.
The seventh step was to conclude the assessment. Based on the hazard, exposure, and control findings, we determined whether the chemical exposure risks were adequately controlled or whether further improvement were needed. The eighth step was to identify the actions that should be taken. Corrective and preventive actions were identified according to the risks and weaknesses observed during the assessment. These actions may involve improving engineering controls, updating work procedure, strengthening chemical safety training, or providing more suitable personal protective equipment. The ninth step was to provide recommendation and assign an action priority. Each recommendation was prioritized according to the urgency and significance of the identified risks. High priority actions should be implemented first because they involve more serious risks or more significant weaknesses in the existing controls. The final step was to prepare, present, and submit the CHRA report. All relevant information, assessment findings, conclusions, and recommendations were documented in the final report. The findings were then presented to the client so that the responsible parties could understand the chemical risk and the actions required to protect the exposed personnel. Overall, this methodology allowed the assessment to systematically identify chemical hazards, evaluate the level of exposure, review the adequacy of existing controls, and recommend suitable risk reduction measures. This concludes the assessment methodology section. We will now proceed with the main assessment findings and results.
Now I will present the assessment findings, beginning with the hazard ratings, or HR, for chemicals hazardous to health identified in the laboratory. A total of 40 chemicals were reviewed based on their safety data sheets, hazard classifications, and relevant health hazard statement. The hazard rating indicates the severity of health effects that a chemical may cause. It is important to understand that HR represents the inherent hazard of the chemical and not the actual level of exposure. As shown in the table, the ratings vary depending on the health effects associated with each chemical. For example, 2-propanol and acetone received lower inhalation hazard ratings because their major health effect is drowsiness or dizziness following vapor exposure. Other chemicals received higher ratings because they may cause more serious health effects. Formaldehyde, for example, received a hazard rating of 5 due to hazard ratings such as carcinogenicity and specific target organ toxicity. The remaining chemical also showed a wide range of hazard ratings. Several chemicals received the highest hazard rating of 5. This included chemicals such as hydrogen peroxide, iodine crystal, lead nitrate, mercuric sulfate, naphthalene, nitric acid, phosphoric acid, and potassium hydride. These higher ratings were associated with severe effects such as skin corrosion, serious eye damage, carcinogenicity, reproductive toxicity, acute toxicity, and target organ damage. Meanwhile, 2-hydroxyacetophenone and zinc powder were recorded as not classified based on the hazard information available in the SDS used for the assessment. Overall, the results shows that the laboratory contains chemicals with different level of health severity. Therefore, chemicals with higher hazard ratings require greater attention, stricter handling procedure, and effective control measures, even when they are only used in small quantities. I will now pass the presentation to the next presenter to explain the exposure rating and action priority.
Next, I will discuss the exposure rating or ER. Unlike the hazard rating, which focuses on the harmful properties of the chemical, the exposure rating considers the actual laboratory conditions. This includes how frequently the task is performed, how long the chemical is handled, the amount released, and the possibility of the chemical being inhaled. The chemicals were divided according to the laboratory activities such as GCMS or HPLC analysis, sample extraction, forensic analysis, synthesis, reagent preparation, and pH adjustment. Most of the exposure ratings range between 2 and 4. Chemicals such as ethanol, potassium hydroxide, and sodium hydroxide receive lower ratings, while chemicals such as pyridine, xylene, dichloromethane, and lead nitrate, sodium azide, aniline, sulfuric acid, nitric acid, and formaldehyde receive higher ratings. Potassium hydride recorded the highest exposure rating of 5 in the assessment. This indicates that its handling conditions may create a greater potential for exposure and therefore require careful control. However, the table also shows that the existing controls for the assessed tasks were considered adequate under observed working conditions. This slide summarizes the adequacy of the technical controls and the assigned action priority. All listed laboratory tasks and chemicals were assigned action priority 3 or AP3. This means that the current controls were generally considered adequate and no immediate major corrective action was required during the assessment. However, AP3 does not mean that the chemicals are harmless or that no further action is needed. It means that the existing controls should be maintained and reviewed regularly to ensure that they continue to function effectively. For example, the fume hood must continue to operate properly, suitable PPE must be worn, and safe chemical handling procedures must be followed. Any changes in chemical quantity, work procedure, equipment, or frequency of use may affect the exposure level and require the assessment to be reviewed. Next, the third presenter will explain the detailed findings on the existing technical, organizational, and emergency controls.
This slide presents the findings on the adequacy of the existing technical and organizational controls. For engineering controls, both the LEV and GEV were operating during the assessment. The LEV appeared to be in good physical condition and was able to remove air from the chemical handling area. However, the chemical storage cabinet was connected to only one extraction point. This may reduce uniform air removal throughout the cabinet. In addition, inspection, testing, and preventive maintenance records for the ventilation system were not available for review. The students were also provided with PPE such as safety goggles, nitric gloves, laboratory coats, and face masks. The PPE was generally suitable for routine laboratory activities. Nevertheless, glove compatibility must be checked against the STS because nitric glove may not provide equal protection against every chemical. For organizational controls, chemical labels and STS documents were available. However, some STS documents had not been updated. Therefore, the adequacy of the safe word systems and practices was recorded as known. Information, instruction, and training were considered adequate because students received guidance on safe handling, PPE use, and laboratory procedures. Personal hygiene practices were also adequate. Eating and drinking were prohibited, proper laboratory clothing was worn, and contaminated materials were discarded in designated waste containers. For emergency response and preparedness, the controls were generally adequate. A first aid kit was available in a visible and accessible location. Firefighting equipment, emergency exits, and emergency telephone numbers and response instructions were also provided. A chemical spill kit was available for minor spills, and laboratory users were aware of the basic actions required during a spill, fire, or chemical exposure incident. However, witnesses were identified for exposure monitoring and medical surveillance. No personal air sampling or workplace air monitoring results were available during the assessment. Therefore, the actual airborne concentrations could not be compared directly with the permissible exposure limits. Similarly, no records were available to confirm whether laboratory users had undergone medical surveillance related to chemical exposure. The absence of records does not necessarily mean that monitoring or surveillance was never conducted. However, it means that their implementation could not be verified during the assessment. I will now pass the presentation to the final presenter for the recommendations and conclusions.
Based on the findings, several improvements are recommended to maintain and strengthen chemical safety in the laboratory. Firstly, safer chemical alternatives should be considered when substitution is practical, especially for chemicals with severe health effects. Activities involving volatile, corrosive, or toxic chemicals should be performed inside a functioning chemical fume hood. This is important because bakers should be controlled at their source rather than relying only on general room ventilation. The LEV and GEV systems should undergo routine inspection, testing, and maintenance. Proper records should also be retained as evidence that the systems continue to function effectively. Gloves, goggles, and other PPE should be selected according to the specific hazards and compatibility information stated in each STS. Contaminated or damaged PPE must be replaced immediately. SDS documents, labels, standard operating procedures, and emergency information should be reviewed regularly to ensure that they remain current and accessible. Regular training should be also provided on safe chemical handling, spill response, waste disposal, and emergency procedures. Chemical waste must be correctly labeled, tightly sealed, and stored in the designated area away from experimental workstations. Exposure monitoring should be conducted where airborne exposure may be significant or cannot be confirmed through observation alone. The need for medical surveillance should also be reviewed based on the chemical used, the possible exposure level, and the overall CHRA findings. In conclusion, the assessment identified chemicals with hazard ratings ranging from low to very high. Although the existing technical controls, PPE, and emergency facilities were generally adequate, several areas still require improvement. The main weaknesses were outdated SDS documents, unavailable ventilation maintenance records, the absence of exposure monitoring results, and the lack of medical surveillance information. Therefore, the laboratory should maintain its existing controls while improving documentation, monitoring, and periodic review. This will help ensure that chemical exposure continues to be controlled and that laboratory results remain protected. That concludes our presentation. Thank you.